Hello guys and welcome to episode 4 of Escape the CAD Overlords series. Now today we will be talking about snap hooks. Snap hooks, man, it's an amazing subject. It used to be that when you have a bunch of electronics and you wanted an enclosure, you had to pay $10,000–$15,000 for injection mold. I mean, it was a large investment. You had engineers specialized in the stuff that would design the snap hooks and all that. Nowadays, with 3D printing, anybody can print a plastic enclosure, so the amount of people that need to design snap hooks is increasing rapidly. Now, large CAD companies have figured that one out, and they're developing tools for automating the snap hook design. I think SolidWorks has them in their premium license, which is horribly expensive, and my favorite one is Fusion. The snap hook tool in Fusion is in the design extension, which you need to subscribe to the extension, to the subscription that you're already paying for. Say that we don't want to be paying this rubbish money and wasting our money away. What do? Well, how did they design snap hooks in the old days? So yeah, let's do what Gandalf did and find a scroll or a paper or a PDF somewhere. So guys, the free software I'll be using today is Acrobat Reader. So I'll be opening a white paper from Bayer Material Science. If you don't know Bayer, they're one of the largest chemical companies in the world. They make everything from paint to the aspirin. And companies used to do this. I don't know if they do it anymore, but what Bayer did here is it helped you get your work done, get your job done, in the hope that you will like them for being nice to you, so that you select them as your business partner, right? So what Bayer is doing with this white paper is basically saying that being nice pays. Mind blown, guys. Anyway, you really need to read this through. It is very important. It is very well written, and when you're done, you will be able to design anything that you might need to design. But today I'm going to give you the quick and dirty, and I'm going to make an example design, and hope that I don't mess it up. And the quick and dirty of it is basically this table, because 90% of snap arms are the cantilever type, right? And Bayer suggests that we use this design, type 2, which has the thickness of the arm reduced down to half at the end, right? They say that this is a more efficient use of material. So we'll be doing a rectangle cross-section with the type 2 design arm. And for this, we have this equation. Now, what does this equation tell us? This is the equation for the maximum permissible deflection of the snap arm, right? There's a coefficient here, 109 times epsilon times length squared divided by h. So what is epsilon? Well, we've got this legend here, but there's been a slight failure. So epsilon is this E, right? It is the permissible strain. So what this means is that if we strain this snap arm more than this, it will deform, and we don't want that. I will show you how to choose this epsilon value in a bit. Then L is the length from the root up to the tooth. It shows it here in the type 1 type of design, but it doesn't show it here because they didn't have the space, presumably. But that is what L is. And H, well, that's the thickness, right? You see it here in our type of design. It goes down to half at the end of the arm. So with that, let's jump into Alibre and show you my approach to snap hook design. I'll make a new part here, right? I'm going to call it snap hook type 2, right? And I'll start a sketch on the YZ plane. Now I want to start drawing somewhere in open space. You will see why. So I'll make something that looks like that's not what I want to end up with. Say that this is 3 millimeters. So Alibre just scaled everything. That's an option. You can have it, you can turn it off if you don't like it. Now I want to say that the top, that thickness is going to be D1 halved. That is the type 2 snapbook arm, according to Bayer's white paper. That's the little tooth that protrudes, right? That is how much engagement I'll get, you know, holding on to the other part. Let's make that 1 millimeter. This will only help longevity, you know, it doesn't wear out too quickly. Let's make this another millimeter, and let's say that we get this angle to 30 degrees and the overall height of it. So the length from the root to the tooth, I'll make 10 millimeters. You know what? Let's make that 15 millimeters. So what I want to do now is I want to open my equation editor, and well, actually, you know what I can do? I can even extrude this. So let's extrude this for 5 millimeters. Again, the sketch is not fully defined. It can move around in space. Some of you may know why, but let's go first into our equation editor, and I want to put numbers here that make sense when I look at them. Sorry, put names that make sense when I look at them, right? So D1 was my root thickness, so root H, that's what the white paper calls it, H. This is length. Okay, let's note that one. And this one, D3 is my tooth engagement. Okay, so now I want to calculate my maximum deflection, right? But in order to do that, I need to know my maximum permissible strain. So let's go back into our PDF. We see here that it says look at table 2. Let's go find table 2. And here we are, right? It gives us a few materials. It says for APAC, which is a commercial name, high heat polycarbonate, that's 4%. Bay blend, which is polycarbonate ABS, 2.5%. Okay, that's all well and good, but how do you get a number for the material that you're using, right? You can Google, and you will Google this. Yield strain. Yield strain is the strain which, when experienced by the material, it is plastically deformed, right, of ABS. You will see here that we get a value of around 3%. So 2.5 that we got from Bayer is okay. It's a logical number. Let's do PLA, right? Let's check PLA. 2 to 5%. Well, here I would take the 2%. So that's how you get your permissible strain for your material. You look for yield strain so that it doesn't deform, right? Or if it's in this table, you use this table. And we go back here and we'll make a scale variable. I'm going to call it E-strain, and I'll say that I'm working with ABS, right? So 2.5 is the maximum permissible strain. I'll use a strain of 2. But I need to divide it, that's the percentage. I need to divide it by 100 because I want the absolute value and not the percentage. Right? So that's 0.02. That's all good. So now I can calculate my maximum deflection. So I'll call this Y max. And the equation, according to the PDF, is 1.09 times my strain times the length squared, divided by the root thickness H. If I click OK, I see that for these values, I'm getting a maximum deflection of 1.6 millimeters. So after that, it will deform. I always want this number to be larger than my tooth engagement, but I don't want it to be a lot larger because, you know, I'm just wasting potential there. So I'll go into tooth and I'll make that 1.5. Seems fine. I'll hit OK. Now here's some secret sauce, guys. So what I'll do now is I'll make this into a catalog feature. And when you make something into a catalog feature, an extrusion or a sketch or whatever, all of the variables that you have used to make it from the equation editor get brought in when you use that catalog feature. But now I haven't used my Y max, so that'll get lost. and I don't want that. So what I'll do is I'll make a line here, a reference line, and I'll say this is Y max in length. Okay, so there's my reference line there. So let's click OK. I'll make the entire extrusion into a catalog feature, and I'll go into my catalog features and I'll call it snap hook type 2. No, snap hook type 2. Let's use it now. So I'll be making an assembly and I'm going to call it enclosure. I'll bring anything else in. I'll start making parts right in here. I'll say this is the bottom shell. Let's get a center rectangle going. 200 by 61, for example. We'll extrude that for 30 millimeters in the reverse direction, and then we'll fillet it using my quick select through the top surface. Let's give it a fillet of 5. Let's blend vertices. I kind of like that. And then we'll shell it for how much? Well, we'll shell it for 4 millimeters, let's say. So that might be the bottom of our electronics enclosure, and then we'll go back in, make a new part, and that is going to be the top shell. Again, we'll do the same rectangle, so 200 by 160. Oh, what did I do? Was it 165? So, and we'll extrude that for another 30, and we'll fillet it around. Now, here's one top tip. Because I am using these fillets, because I'm doing top-down design basically, Alibre remembers the fillet settings from the previous part. Okay, that made my life slightly easier. I'll edit my assembly again, and I have my 2 pieces of the assembly. So now I'll hide my top shell. I'll edit the bottom one, and I want to insert my catalog feature here, right? So this one, I'll just hit apply. Now my snap hook kind of hovers in there somewhere. I need to go into my sketch and tell it where I want it to be, right? So where I want it to be is here. I'll just imprint here, this area, using my trick, and I'll just say this point and these points are coincident. You know what I can even do? Make this into a midplane. Right, there you go. And now I'll just add it again over here. Okay, so it came out with the completely wrong orientation. In that case, what I'll do is I'll hit alignment reference and give it an edge here. That brings it upside down. Let's see if I select another edge, will it fix that? No, well, I can fix that with a rotation of 180 degrees. So that's okay. I go in here and I tell it, look, snap this point, this point. I will do the same thing. We'll just make this into a mid-plane as well. Now we'll mirror things around. One there, and we got one there. We've got our snap hooks on the bottom enclosure, right? Before we go, I want to show you another thing here. If we go into the equation editor, I have both my strain values come in, as well as my Y-max values. And these do not show the equation, but they show the correct value. So at least it can inform me of what is going on. And even though it's not showing the equation, if I change something here, you'll see it changed there. So that's all good. Okay. Now I'm going to go to my top shell. So what do I need to do? Let's keep this showing. What do I need to do here? Well, first of all, I'll hit visible edges. It's the same hotkey and trick I use to select through surfaces. And I'm just going to, in here, create a pocket for this. Now, because I'm using the shaded in all edges view, I can see the other part. Okay, so again, benefits of top-down design. I'm imprinting this surface, and I'll do this. Bring this in like so. And I also want to have these 3 in as references. I want to add a tolerance here of a 1/10. Okay, 2D sketch. Sorry, I want these 2 to be parallel. I want to make a line here as a reference that I can dimension this to be 1 millimeter. Okay. So no, that's not enough. It's too much. 2 millimeters. I'll have another tolerance here of That's D5. So I'll say that this one is half of D5, and if this one is D5 again, then I'm gonna get a line going here. So what I want is, and I'll get another one line, horizontal and a reference. I'll get a line going from here to somewhere close to here. Give this an angle of 4. Alternatively, I could have dimensioned this. So what is this? This top reference line shows us where the slope on the tooth starts, and this one shows us where it ends. So what did I do? I just made a slope here so that when I hit that, I get a more gradual deflection of that snap arm, right? That's all I did. So now I need to complete this sketch, and I need to cut it. We'll go mid-plane because that's how the snap hook's made. So the snap hook was 5 millimeters, wasn't it? We'll give it some wiggle room. I'll just say 5.5. That's good enough. You know what? I can even go 6. I don't want to view all edges anymore. And now I'll show you another little trick. So first of all, oh man, I didn't shell before I did all of this. So we're using a parametric CAD software. So this dog bone here, this line, is our time travel lever. So we pull the time travel lever, we go back into time before our extrusion, and we make our shell. And then we come back in today, and we see that we broke everything. So I guess what we could do here is this shell could be thicker. Will that work? Yeah, that'll work. And what's the thickness that we get here? 0.5 mil. That works. Okay, so in the bottom shelf, we just added another one there, and then we mirrored. I'll show you. I remember that I did this for a Two-Tool Toby competition. So how do we add the cutouts without doing them all over again? Well, just go here. All right. Let's look at it this way. These two lines are fine. We're going to imprint them, and we're going to get an ellipse. We'll go from center point there to center point there. Let's make sure that this is fully defined. Okay, that's it. Now I will path pattern this feature 4 times using this path. Voila! Right? You can mirror this because it's not a rectangle, but yeah, I was too lazy to do it again. Being too lazy, often makes you discover the coolest tricks. Look at this. Look at what happened there. I guess a remove face could work there. Yeah, there you go. Still works. Okay, that's so cool. So we go back into the enclosure. You know what? I'll just make the bottom shell. Just change the thickness in the bottom shell as well to 5, just so that they look, they're more in tune with one another. But guys, look at what we have here. We have an enclosure that could very well be an electronics enclosure with 4 snap hooks, and they're designed perfectly, and we know what's their maximum deflection. We know they will not break. We can even calculate the force you need to open them, or the force you need to push in. Fully engineered snap hooks, and we have them as a catalog feature now. We can be dropping them in wherever we want. And you know what? Let's be honest. I could have made the pocket into a catalog feature and saved even more time. And in any case, with that, that's the conclusion of our video. If you liked this one, hit like. If you really liked the elliptical pattern trick, let me know. And if you want more like this, hit the subscribe button, and I'll catch you in the next one. Cheers.